We are very happy to have our first speaker, Jun-Muk Hwang from IBS Center of Complex Geometry in Daejeon. So he will talk about varieties of minimal rational tangents on cubic threefolds. Yeah, please.
Okay. Do you hear me? Okay. All right. So I'd like to thank the organizers for the invitation. I'm very happy to visit Taipei again and see many friends. Okay. The topic of my talk is minimal rational curves. So if you know me, I have been interested in this minimal rational curves for a long time. But let me recall the definition. So the definition is you consider a projective variety in some projective space. And then I choose a non-singular point. Then I consider what I call minimal rational curve. Through X. This is just means, of course, it's on X. It's a rational curve of minimal degree through X. Okay, that's the name. Now, I've been particularly interested in in tangents to such curves. So this is the concept of variety of minimal rational tangents. At X. This is a projective variety, not necessarily irreducible, in the tangent space, in the projectivized tangent space at X. And it's defined as you collect all tangents to minimal rational curves. So C in X is a minimal rational curve through X. Of course, to make sense of the tangent space, you have to consider those which are smooth at X. And then you take its closure. So it's usually all minimal rational curves are tangents at X, quite often. But anyway, if it's not, you just consider those minimal rational curves which are smooth at X and then take closure. That's the object I call variety of minimal rational tangents. And usually I abbreviate it by VMRT at X. And I'm interested in looking at it as a projective subvariety with a natural embedding. And the projective geometry of this subvariety quite often tell you about the intrinsic geometry of the original projective variety. So that is the viewpoint. So today I'll just look at very special examples of this. And let's start with the most well-known case. This is cubic threefold. So maybe I better write this way. So this is cubic threefold. Which is very well known. Now if you choose a general point, then a line of P4 through X lies on X. Because it's defined by cubic equation, a line through a point is contained in X if and only it has order of contact bigger than 3 with X. Okay. So for this reason, it's easy to see that what is VMRT? This is exactly, this is, well, now this is of course P2, so it's a subset of P2, and this is a complete intersection. Of type 2, 3. It's defined by a quadratic equation and a cubic equation. This comes from second and third derivatives of local defining equation of X. It's a hypersurface, so it's a local defined, it has a local defining equation. And then you take second and third derivative. If they vanish, it must represent a line because of this. So the VMRT in this case is something very simple, intersection of quadratic and cubic on the plane. In particular, this says that CX is 6 points. It consists of 6 points on a conic. And which we call Rx. So there is for general points, there is a conic, and the VMRT is just 6 points on a conic. And in particular there are 6 lines on X through X. Through the general point, there are exactly 6 lines on cubic threefold. Okay. Now, this means that on a Euclidean open set neighborhood, so you can choose a Euclidean neighborhood, lines on X give 6 distinct fibrations. To some surface, it's a complex manifold dimension 2. Okay, so here you have X, and you choose a general point, and there's some neighborhood. And on this neighborhood, since there are 6 lines through each general point, okay, one more. There are 6 lines through each general point. There are, at least in this neighborhood, you have 6 fibrations. Yes. But so the neighborhood is necessary to give a numbering, also to have fibrations, such that so you can have these fibrations such that for each point in the neighborhood, the VMRT is just tangent to the fiber. fibers of this map. So, okay, so they are just the fibers of this map through that point. And this means that, and this Cy in Ry now is an ordered 6 points. On this Ry, which is P1. So just considering a neighborhood, you can order the lines. And then, so this implies that you have a holomorphic map. It just means it's a line. It's one-dimensional. The kernel of derivative is one-dimensional.
So this Cy has nothing to do with Cx?
When y is the same as Cx, if y is x. Am I confusing? So y is a point in a neighborhood of u, and x is a neighborhood of u.
Yeah, but I mean Cx was just 6 points and Cy is a line.
Well, it's not a line, it's a point. I'm taking projectivization of one-dimensional. Okay, sorry about the confusion of it. I'm just rewriting this. I'm just rewriting this. These are 6 points. Okay. So this is an ordered 6 points on conic. And so you have a holomorphic map from the neighborhood to M06. This is moduli of 6-pointed projective line. So you have a natural holomorphic map in the neighborhood of each general point to M06. Now I was interested in this map, but then I learned later that this map was already considered long time ago. So there was a question. This question. So I was interested in this question and then learned that it's already asked by Griff series long time ago. In 1979, in their paper on local differential geometry and algebraic geometry. So the question was, is phi injective? So that is the question. So in other words, the configuration of lines through general point. As you move the point, whether this configuration as a moduli of a 6-pointed line, whether this changes in the maximal possible way. So, by the way, this dimension of M06 is also 3. So they have the same dimension. So if injective, it means that it's locally immersion. It's biholomorphism. So that is the question. And this question was already answered before I even thought about the question. But only personally I learned about the answer much later. But this was answered by Jennings. In 1987. And what he proved was that phi is injective for a general cubic threefold. So if you choose a general cubic threefold, this map is indeed injective. And the general point. Now, how did he prove this? Actually, he was a student of Mark Green. So this was his sort of thesis on the Mark Green. So to prove this, it suffices to Jennings' proof. Of course, it suffices to prove it for check for one specific cubic threefold. Then by deformation, it's true for general cubic threefold. And the way he did it is moving frame computation. Projective moving frame computation for specific cubic equation for which the computation becomes simpler. So in his case, what he did was this x0 square x4. I'm just writing it to give you the flavor. You don't have to, the equation will play no role. So don't worry. So this was the cubic hypersurface in P4, where x0, x4 are the homogeneous equations. So he considered a general, or this special cubic hypersurface and checked the moving frame, project moving frame, and computed the derivative of this map and showed that it's indeed injective. All right. You are right. You are right. Or maybe there's x0. Okay. So that's why I told you not to worry about this. It will play no role. The coefficients are. Xi. No, isn't 3 the same? Okay. Square. Okay, don't worry about it. The important thing is the coefficients are chosen such that it simplifies the moving frame computation. I mean,
If you take not this, but the segregate.
Oh, you have, don't say anymore. Because you spoil my talk. So the question was exactly, I was interested in this question, and then I learned about this answer. It was answered like this, but it was not so satisfying to me because it somehow doesn't really tell me why it's really true, why this map is really injective. So I was looking for some more geometric explanation of this. And so exactly what, as Gabi suggested, so is there a cubic threefold for which the injectivity of phi is obvious for some geometric reason. So that was what I have been thinking. But my mistake was I usually worked with smooth manifold. So I avoid singular hypersurface. I'm kind of a smooth guy. I don't like singularity. So I try to ignore singular cases. But among smooth cubic threefold, I couldn't really find such example. So for a long time, I was not very happy with this problem. But then early this year, in April, there was a conference in Beijing. And it's Mukai Sensei in Beijing exactly before Gabby told me. Mukai Sensei. So in Beijing, I heard about Mukai's lecture. But this is not a talk on Segre cubic. So this is a special hypersurface, cubic hypersurface. In P5, you can write it in P5 instead of P4 by this equation. So it's a very special cubic hypersurface. Equals 0, yes. Thank you. And it has many interesting properties. So let me recall what was the properties.
But it is just variation to M06, right?
You are also spoiling me. But please wait. Maybe the three-dimensional case is sort of obvious to you, but let me, I just repeat what I discovered, okay? And these properties of this Segre cubic have many beautiful properties, but the first one, I think the unique cubic threefold up to isomorphism with 10 nodes. So that explained why I didn't pay much attention until this April. Because whenever there's singularity, I didn't like it because rational curves, when there are singularities, behaves very strangely sometimes. And then there are interesting properties. There are exactly 6 distinct irreducible family of lines covering S. So in particular, you can order them globally. So there is now a Zariski open set. And this map we considered S. This map we considered is now well defined on this Zariski open set. And then, as Saja mentioned, S is the GIT compactification. Of M06. So in particular, there's a natural inclusion. So M06 is naturally embedded in Segre cubic. And so this motivates the first kind of result. Maybe I call it result, but maybe it's known before, I don't know. Theorem, this is theorem for M06. So now you have this Zariski open set inside the Segre cubic, and you have this map, holomorphic map M06, which is naturally contained in S. So the theorem claims that the composition is the inclusion. U in S. So in particular, phi is injective. So this is more sort of, to me at least, more satisfying answer. It's kind of, by geometry, but the proof, of course, I have to explain, but it gives a more conceptual explanation why this map phi must be injective. Okay, so then after this, I will try to generalize it to higher dimension. So let me state the higher dimensional version. This, I don't know whether this is stated before, but the proof of this case, this special case is also sort of, you can see it from other works. And one I heard is from Mukai Sensei, told me there was one Koike. Yes. If you analyze his result carefully, then it implies this. It's more along classical, but only in this case, M06 and case. In this case, the 6 points on P1, it corresponds to some hyperelliptic curve, and then there's a tumor construction, and you can recover this VMRT from that. So there's another more classical explanation for this. It's a global statement about Segre cubic. About Segre cubic. Okay, yes. Yeah, exactly. If it was a smooth cubic, you could never realize this. But so that's why. Yes. I think it's the same as, for smooth cubic, there's no rational map. There's only from this open set, only from some for some Euclidean neighborhood. Because you cannot order the 6 lines globally. Yes. So in this case, all the lines are distinct. There are 6 distinct lines. But for smooth cubic, they are usually irreducible family. There's monodromy going on. So you have to consider, instead of M06, you have to consider its quotient by symmetry group. Yes.
Actually, in this case, you can even say more, because there are 6 small resolutions of singularities of S, which have a structure of a P1 vibration over a integrated surface.
Maybe that's part of what he examined, yes. But let me not, let's forget about it now. It's something, there are many different ways of approaching this. Now I'd like to tell you about higher dimensional version of this. So generalization. So now we look at M0n. So this is modulo of n-pointed lines. And then there are these forgetful maps. There are n forgetful maps. You forget 1 point from each collection, and then you get a holomorphic map or regular map. So you have sort of, this is M0n. And there are now n fibration, F1, F2, Fn, all going to the same target, but different maps. So if you look at 1 point, now there are 6 n different fibers. Okay. So let's consider these fibers. Let Fx exactly as before. We just take the fibers of these maps. This is tangent directions at that point. So these are, this is Fx, this is just now n points in P, which is now P n minus 4. So these are now n points on P n minus 4. Now here's our sort of result. So this is sort of the main theorem this talk. Which I hope was not known before, but for general, so n is equals to at least 5. For general point, first, there exists a unique rational normal curve of degree n minus 4, which I write as Rx inside the tangent space. There's a unique rational normal curve of degree n minus 4 inside the tangent space, such that this Fx is contained in this rational normal curve. So at this point, if you look at this general point x on M0n inside the tangent space, there are now, we know there are these n points. So these are n points. These are n forgetful fibers. And what the theorem claims is that these n points are contained in one rational normal curve. They lie in one rational normal curve. Now, this standard fact that if you have n minus 1 points in P n minus 4, one less, then it determines a rational normal curve of degree n minus 4. But here we say that there are actually n points that lie on this rational normal curve. So this is a restriction on the configuration of the point. They must be contained in this rational normal curve. And two, the n-pointed P1. So we have now Fx is inside this rational normal curve, which is P1. So this is n-pointed P1 is of moduli. So this belongs to a point in M0n because it's n-pointed line. And this is of moduli exactly x. So by looking at this tangent to the fibers, you obtain a P1 with n-points on them. And the moduli of this P1 with n-points on them is exactly that point itself. So that is the statement.
So this is just the universal force, right?
Universal, yeah, it becomes universal at general point. I don't think it's at everywhere. At general point of MJ. I didn't check. Anyway, maybe you are right. But this is birational to universal curve. I don't think it's at everywhere. Because at some special point, there's no reason that this is unique. This
this property 1 is satisfied by the general set of n points.
Yes.
In
and points in, yes.
You are saying that these n points are general enough so that there is a unique.
Yes. So that's a restriction.
This looks just very similar to the Kapranov's description of M0.
Yes. It's actually, it's a different. Yes. I will maybe after. Why don't you wait, Sasha? Why don't you wait? I will explain the relation to that. Okay. Anyway, this is the result. Now let me tell you why this is a generalization with this. You need some explanation. Why? Here we looked at lines, tangent lines. And here you have this more general moduli theoretic statement. So the facts, I will recall some facts. The facts is, these are collection of results. I think in modern publication, this is the first guy I know. Euro, and then Kumar. And most recently, Bullock, Naji, Massarenti. So first of all, the GIT compactification. Of M0. M, which we write as Vn minus 3. Has a natural embedding. In some projective space, such that the closures of fibers of this forget to map are minimal rational curves. And they are lines, if n is even, and conics if n odd. So these fibers of this map can be compactified to minimal rational curves. On some, actually these are Fano varieties. When n is even, it is a singular Fano variety. When n is odd, it is smooth Fano variety. And these fibers of Vogel maps are exactly minimal rational curves. So one can see that this Fx, the fibers of Vogel maps are exactly this VMRT in this case. Vn minus 3. So in that sense, this result is a special case of this result when n is 3. Okay, and the proof is relatively simple. So let me just give you the idea of proof. Of this main theorem. And you just use this this construction, so which was also used by Kaplanov. But I think this was this part is much more classical. So this I use the rational map. So there is a rational map from Pn minus 2 to Vn minus 3, I mean to M0n. But the dimension is one-dimensional fibers with one-dimensional fiber. So defined as follows. And the reference I know of this map is actually this guy, Bureau. But it's probably known before, maybe in the 30s. Because I saw some name called Room. I don't know, I couldn't check this reference. But there's some very old, they considered this map. I mean, what Kaplanov did is he considered compactification as a dilemma-Mumford compactification using this map. So the part about smooth locus, what's happening on the M0n itself is very classical. And this map is defined as follows. So fix n general points. Yeah, from here is, you can see also in Kaplanov's paper. N general points in Pn minus 2. And then for general point, let Ry be the unique rational normal curve of degree n minus 2 through So you have n minus 1 points on Pn minus 2. So there's a unique rational normal curve of degree n minus 2 through these points. And then this map, then Phi is defined a rational map from n. And it's defined as it sends this general point y to the n-pointed projective line. N-pointed. This P1 is Ry. So it sends the given point to this n-pointed P1 Ry. So that's the point in M0. So that is the map. And this map, the fiber of this map is obviously when y moves along Ry, it gives the same n-pointed P1. So that's why the fiber is one-dimensional. So the fiber is, so roughly speaking, the fiber of PC, these Ry's. So we use this map to prove the theory. So the only interesting point is why there's a rational normal curve of degree n minus 2, but it becomes degree n minus 4. That's a very simple geometric factor. So the only thing to check is this. Check fibers. These forgetful maps. Through this point, this y, are images of the lines. So the line is y, a1, So these are lines in Pn minus 2 on the PC. So this rational map sends these lines on Pn minus 2, joining y to these endpoints to the fibers of the forgetful map. So that is the main point. So this implies that the unique rational normal curve of degree n minus 4, which is in Ry, where x X is now the image of y, is the image of Ry under the projection from the tangent line. At y. Yes. So this is a rational normal curve of degree n minus 2, but there's a projection from a line. two-dimensional projection. And that cut the degree to n minus 4. And this, almost by the construction, the image Rx, yes, image Rx must contain the corresponding points, the fibers of the forgetful maps, and their moduli is just this. So once you use this map, the proof is pretty simple. Now in the remaining time, let me raise a question, because I'm not so, apparently there are many experts here on more classical geometry. So I'm curious about what is other possible generalization. Because I think this is one special generalization in terms of M06 of the result about Segre cubic. But there are few cases I'm curious, and which maybe the experts can tell me. So I have a few questions. For example, one question I have is there a hypersurface over degree n in Pn plus 1 with n factorial distinct families of lines. Covering X. So this is another generalization of Segre cubic primal. For cubic, when n is 3, there are Segre cubic primal has 6 distinct families of lines, so that we can define this map, the moduli map of VMRT as a global map. And the reason I'm asking this is that Jennings, okay, thank you. I already learned. Jennings' result applies to this as well. So this injectivity of the moduli of VMRT also works actually for any hypersurface, if you interpret it suitably. So in particular, we know that for general hypersurface of degree m, there are n factorial different lines through a point, and the moduli of these points vary maximally according to Jennings. So I like to know whether there's a similar construction as a Segre cubic primal, where we can use this to check this injectivity. So that is one question. And another possibility is Segre cubic itself. So there's a higher dimensional Segre cubic. So higher dimension. Which is defined by, in the same way, Ti 0 to now what, n plus 1, n plus 2 maybe. And in this case, also Jennings' result applies to higher dimensional cubic. So the VMRT in this case is, again, is VMRT is a complete intersection of type 2 and 3, because it's a cubic hypersurface, the same complete intersection time. And we know that for general such hypersurface, cubic hypersurface, the map is injective by Jennings. So, but for this case, for the Segre cubic case, whether there's an explanation of injectivity of of this the moduli map for VMRT. I don't know, I cannot so far. These are the two questions. If you are interested in more differential geometry, there are differential geometry questions. So let me, since I have 1 minute, let me mention this. So this main theorem tells you that there is a natural, what people call GL2 structure on a Zariski open set. In M0n. GL2 structure means that rational normal curve in each tangent space. That's GL2 structure. In other words, there's a rank 2 bundle, W on U, such that the tangent bundle of U can be naturally decomposed into symmetric product of what? So there's natural decomposition of a tangent bundle into symmetric power of some rank 2 bundle. And it carries differential geometry. So the question is, and such GL2 structure has natural connection. The question is whether this connection can be used to recover these forgetful maps. So they have natural connection. So it's an interesting question. What's the differential geometry property of those connections? Thank you.
Oh, thank you very much. Are there any questions? Yes.
I don't quite understand your isomorphism. What are the dimensions of the
This is n-3 dimension. This is in M0n.
So you use dimension n-3, but
This,
you use dimension 2 n-6.
let me see, maybe I'm confused. I will use. If you take n minus, this seems correct, okay. Let's take the case where n is 6. Then it's symmetric scale of rank 2 bundle. So it's correct, it's conic. It's corresponding to conic. Symmetric scale of rank 2 bundle. So this has rank 2. So if you take n minus 4 symmetric power, it's n minus 3. Yeah, n minus 4. Sorry. No, it's symmetric power of 2-dimensional vector space. So it has dimension n minus 3. What I mean is symmetric power of each fiber of the vector bundle.
What is the, can you repeat the last sentence you said? So there is connection. What do you want this connection to computer algebra?
There's a natural connection. So I like to, this connection probably has torsion and curvature. These are holomorphic connections. It's not flat. They must, probably not flat, maybe flat, I don't know. But my hope is that maybe this the curvature of this, or torsion and curvature of this structure recovers this n point. Recovers. For example, in dimension 3, there's conic, meaning that there's a conformal structure on cubic threefold. And whether the conformal structure can recover the lines from differential geometry. That's the kind of, it's a kind of curiosity.
Coming back to the original situation of the smooth cubic threefold.
Yes?
Globally, you still have a rational map to the modular space of, from the cubic to the modular space of 6 unordered points.
Yes, yes. Yes, yes. I used to know. But I think it's the same as regular cubic. So it must be 6. I expect this, yes.
Are there more questions? So if there's no more question, then next is Jun-Muk Hwang again. So thank you very much.